I forgot to change that setting. All right. So first thing you want to do is identify, well, one of the first things you want to do is identify the appropriate u, but in doing so, you may want to change the format of the given equation or function. All right, so we have y equals the square root of x squared plus 3. I prefer not to have a radical in there if possible, because I want it to be as power rule ready as possible. All right, possible. So y equals the square root would become x squared plus 3 to the 1/2 power. All right. Now, I was mentioning this last time, but what ends up being the case often is that when you're first learning this, it's like, okay, well, how do I know what the u is going to be? So what do I make the u? All right. Well, you only have so many choices, but each choice takes you down a different path. Sometimes that path can be a short path, and hopefully that short path is the correct path, because then you get the problem done completed quicker. But sometimes that short path is incorrect, and it's like, okay, the one you're hoping was not the correct path is the one that is the correct one, and that's the one that takes you like 20 minutes to do. Right? Sometimes the problems are beefy, you know. None of these are that bad, but you'll see some before it's all over where you're like, oh, okay, I know what he's talking about now. All right. So what we're going to do, again, going back to those parent functions, is start thinking about, okay, well, what kind of function am I looking at here? Am I looking at a power function? Definitely not a trig function, definitely not exponential, because I don't see a variable in the exponent. No logs, nothing funky here. I'm looking at something that, you know, if this wasn't here, you know, if this were just x to the 1/2, it would be very easy to do. It's not x to the 1/2, it's something else to the 1/2. So let's let that something else be the u and see where that takes us. All right. If that something else, that x squared plus 3 is the u, then y would have to be, by reverse substituting, u to the 1/2 power. So at this point, you take a look at what you have. You don't really do anything yet. You just take a quick look and say, is this something that I can take the derivative of fairly easily? All right. The idea is that it should be fairly easy to differentiate or take the derivative of the equations that you just wrote out. All right. If the answer is no, maybe it's just a hard problem, but most likely it's that you picked the wrong thing for you. All right. Like, for example, let me get rid of this for a second. I'm going to just cut it. I'll put it back in. Let's say you thought the u was, I don't know. Somehow you're just looking at the ingredients that you have here, and you're like, all right, well, maybe it's going to have the 1/2 in it. Maybe my u should be like 3 to the 1/2 power. So you'd look at that and say, okay, I think it's 3 to the 1/2. I mean, there's no basis in mathematics for that to be even possible, but let's say that's what you think. You take a look at that, and when you go to write your y equation, at this point, you should say, okay, I'm on the wrong path, because where am I putting the u? All right, even if you incorrectly thought that you could just replace this with a u, you don't have anything meaningful here, because each one of these equations needs to be a function of a single variable. All right, that's not the case here. This is just a disaster. But fortunately, the disaster happens very quickly, so that you know you're on the wrong path. And you say, okay, well, let's get rid of that, and then try something else. And eventually you come up with this. The problem is, when you're first learning this, there's more false starts. It's frustrating, but then you get the experience. You don't fall into those traps anymore, because you see a problem and it's like, oh, that was just like the last time I did a problem that had, you know, like you'll see a problem, square root of x squared plus 4. You'll be like, oh, okay, now I know how to do that one now. And in a lot of ways, calculus is sort of a brute force subject area, because if you get it intuitively, that's great, you're set. If you don't get it intuitively, you just try as many problems as you can. Eventually, you'll have experienced every problem in creation, and you'll get them all right anyway, right? So honestly, I mean, even when it's really bad now, even when I try to create my own problems for tests, it turns out that I've created a problem that's already created. Right? There's nothing new out there, right? Except like my basketball, golf activities, and things like that. Those are all I make those myself. There's a moment of pride right there. All right. So we take the derivative of each part, 1/2 u to the negative 1/2. Du dx would be just a 2x. We put it all together, but in the process of putting it all together, we substitute the u out and the x squared plus 3 in. All right. So remember, the theory behind this, or theorem, was dy dx is equal to dy du times du dx. All right. Mathematically, that makes sense, because if you were to just take these two ratios and multiply them, the du's would cancel, you'd get dy over dx. But we don't want to do that. We actually want to replace the dy du with the 1/2 u to the negative 1/2, replace the du dx with the 2x, but to save a step, we say, all right, well, we know that the u really is x squared plus 3, so that's what I'm going to do. I'm going to replace the u along the way with an x squared plus 3. And that'll be my dy dx. And that's my derivative. All right. Now, number 6, I wrote out last time, I wrote out the first step just to kind of get you started. Well, first step and a half. The key to any chain rule type problem, I think anyway, I mean, I guess there's a few keys, but like the one main one, and this applies to a lot of differential and integral calculus. So from here on in calculus, is recognizing what kind of problem it is. So when you look at number 6, you might look at it and say, oh, fraction, it must be a quotient rule question. Well, it could be a quotient rule question, but it would be a quotient rule with chain rule inside of the quotient rule. All right, that doesn't sound like too much fun. All right. But if I take that x squared minus 2x to the third power and move it up to the top of the fraction, remember, you can move from one part of a fraction to another part of a fraction as long as you negate the exponent. Now I just took it and made it strictly a chain rule problem. All right. So I made it a 2-rule problem into a 1-rule problem. All right. That's a win. All right. So once we do that, it's along the same lines as number 5, where you have something raised to a power. We're starting to get, hopefully, a sense of what's going on here. If you have an expression raised to a numerical power, the expression is going to be your u. All right. So then differentiate dy du would be equal to negative 3u to the negative 4th. Du dx is equal to 2x minus 2. Put it all together. Dy dx, while also substituting for the u. So we're bringing the u back. Negative 3 times the u, the whole u, to the negative 4th power times 2x minus 2. The u itself being x squared minus 2x. All right.
Will we ever have to like simplify this down?
You will, but not because I'm telling you to, but because you'll want to. You'll, when a question says find the second derivative of this function, and you get this after the first derivative, you're going to say, all right, well, let me clean this up a little bit before I move on, you know, but not for the sake of simplifying. All right, number 7 and 8 is where we start mixing concepts together. All right, 7, it's kind of weird to look at, but it's got a structure to it. Well, 8's kind of weird too, but 8's sort of it's not a trick question. It just tricks people, all right? Because it has the same kind of look and feel as 5 and 6, but it's a different type of problem. Right? And I'll walk you through that in a minute. But 7 is a chain rule within a chain rule kind of deal. Right? Some people call it double chain rule. It's all chain rule, right? Because if you think about what a chain would look like, I mean, how many times do you see something that's called a chain that only has 2 links? Right? Most of the time, it's got a bunch of links. So what we're looking at here, when we have only 2 multipliers, the dy du and the du dx, that's only a 2-link chain, right? When we multiply, this is the link, the multiplication is the link, right? But it is possible that you could have 10 functions composed together. Just because you haven't done that in the past doesn't mean it's not possible. There's no end to how many functions you could put inside other functions, except if the main function, the f function, is a constant, there's nowhere to make a substitution. But as long as there's a variable, there's a substitution possible. All right. What we're looking at here in number 7, even though it's kind of, like I said, weird to look at, is cosine 4t squared. I mean, for now, we're just thinking about t as a replacement for x, all right? T and x synonymous because it's a function of t instead of a function of x, all right? But later on, I mean, actually, we've already done it with the variable t, x, y, t, a parameterized equation, parametrics, all right? That's possible, all right? We could have that as a third variable, but for now, it's taken on the place or the role of x, all right? This whole thing is raised to the 3rd power. So what we have here is a function within a function within a function. So we gotta break it apart extra. Whenever you raise just a trig function to a power, that's the notation for whatever is contained within the trig function to also be raised to the power. All right. So I write it like this. If they give it like the way it was printed, I write it like this, the handwritten way, just to make it a little bit more obvious to myself. What is the innermost function? What's the outermost function? All right. So you almost sort of have to blur your vision a little bit. Now, fortunately for me, that's easy. Done. It's still pretty terrible. All right. But you have ultimately something being raised to the 3rd power. That something is pretty hideous. All right. So let me blot that out there. All right. That parent function looks like it's an x squared parent function. All right. It's power function. Right. It doesn't matter how complicated it is. It's just something being raised to the 3rd power. So that's what my u is going to be. That's something. Where the y would be the u raised to the 3rd power. And then you could do just a quick mental double check. If I replace the u with the cosine of 4t squared, would that get me back to the original function? Yeah, absolutely. All right, so it sounds like it's pretty much the same as what we started with, except you take a look at your cosine 4t squared. Remember what I said before. When you take the derivative, in this step here, it should, or when you go to take the derivative, it should be something that you look at and say, oh, I could do this fairly easily. All right. The u cubed, perfectly fine. Cosine 4t squared, that might be a problem. All right. So what we can do now is define a new variable. Instead of having cosine 4t squared, let's go back to the parent function. If only this was cosine of x or t or whatever. If only it was cosine of x, I could take the derivative of that very easily. It's not. So I got to make a change. And that change would be to define a new variable, letting the 4t squared be, you could let it be whatever you want, but typically we would go with v. All right. So now u would be cosine of v. Now, depending on your penmanship, you may want to choose a different variable. Personally, I mean, when I'm in a rush, my U's start to gradually look more and more like V's. And then I confuse myself and I screw it up just basically because my handwriting stinks. If you're better than that, then go for it. If not, then maybe U subscripts or S's and R's or something. Because that's also a function embedded within another function. So if you have a function that's in another function that's composed, in order to decompose it, you'd have to pull the inner function out, bringing one function back to the parent and creating a new separate equation. Now, as we go forward, and some of us are already there, you can look at cosine 4t squared and say, oh, I know the derivative of that is negative sine 4t squared times 8t. Like if you know that, then there's no need for this extra step. But it's a procedural approach that allows you, no matter how complicated the innermost function is, to be able to get it right every time. Right? So it's very regimented, but for the most complicated types of problems, it's a very effective technique. For the simpler problems, you're going to find yourself just kind of gradually moving towards other approaches, right? If not already. Right. But looking at what we have now, we have simple, simple, and simple. Fairly simple. We could look at each one of them and say, without really much effort at all, I can take the derivative of every one of these. All right. dy du, 3u squared, du dv, negative sine of v, and dv dt would be 8t. But ultimately, I want to get a dy dt. Now, previous problems, I wanted to get a dy dx, but that was because the independent variable was x and the dependent variable was y. Now, x is taking on the role, or t is taking on the role of x. So what we would be looking at is, I mean, it's not really a new rule, but I'll kind of frame it that way. dy dt is going to be the product of dy du, du dv, dv dt. And I can tell you, it's not really so much that you need to memorize a rule or know this rule. It's more that the ratios that you come up with through the differentiation process should simplify through multiplication to give you the desired ratio, which in this case is dy dt. All right. So if I look at this and say, all right, well, what would happen if I multiplied dy du by du dv by dv dt? Well, the du's would cancel, the dv's would cancel, and I would be left with just dy dt, which is ultimately what I'm looking for. All right. So we know we're in a good spot if we multiply these three ratios together. So that tells me I can take my three expressions, multiply them together. So I'm going to have a 3u squared minus, or times, sorry, negative sine of v times 8t. And I know I'm going to have to make some substitutions. So I just leave parentheses for any variable other than t. I think that makes sense because if I know I'm going to make a substitution, then why write the value just to change it in the next step, if that's the only thing I'm changing? Like, for example, that negative sine of v, well, v is equal to 4t squared. Thank you. Let me rewrite. All right. That 3u squared, that u is cosine of v. But I don't want to write the v. because V is, well, most obvious statement of the new year, that V is not a T. So I don't want to write the V. I'll write what V really is. Doesn't really look very peach-ish, but it's 4t squared. So two multiplication symbols. There's three factors, two products involved, two links to the three parts of the chain. So it's a lengthier chain. I mean, if you simplify, you can make it look a little bit nicer, but it's still the chain rule. It's just there's more function to be expanded upon. And the crowd goes wild. Now, number 8 doesn't involve a trig function, but it does involve a product. All right. So the chain rule part of number 8 is actually pretty easy. But there's more to it than just find a U and go from there. Although there is a strategy that would allow for that. It's just, it makes things more complicated than it needs to be. Right. And it involves doing the algebra that you would probably do if you wanted to avoid any rules to begin with. Like in theory, you could take that 3x minus 9 and distribute it out. Remember good old Pascal's triangle? Yeah, or remember the moment where we realized that we didn't want to always have to use Pascal's triangle because it's somewhat lengthy. But for a power of 3, it's not too bad. Power of 10, you're going to be at it for a while. All right. So, but in this case, using a rule, actually 2 rules, is going to get the job done more efficiently. All right. So first thing I'm going to do is rewrite this problem in a more obvious way. All right. Now you can, there's actually 2 ways that we could use this U substitution technique to go to the next step, but I'm going to just sort of focus on one way, and then maybe I'll just draft out the other way and make it available, because I don't, it's confusing enough, so I don't want to make it unnecessarily confusing. All right. So, but this is a product. We're looking at a product between 2 factors, or product of 2 factors. So this is my first factor, my second factor. Whenever you're multiplying 2 factors and then you need to find the derivative, you could do one of 2 ways. You can actually multiply them out, which I already established is going to be a pain, or you could use the product rule, right, which is where you take that first factor, multiply it by the derivative of the second factor, and add to that the second factor multiplied by the derivative of the first factor. All right. So we have these 2 individual factors, all from that those pages that I asked you to complete. I forget what they were, but like 7 through 9 or something like that. But the first function or factor in this case multiplied by the derivative, I'm going to use the notation here, the derivative of the second factor plus the second factor multiplied by the derivative of the first. That's what your f prime of x is going to be. So I'm taking my first factor, which happens to be a function, multiplying it by the derivative of the second one, adding to that just the second one the way it was originally, multiplied by the derivative of the first. In this process, we have to now find the derivative of each of those individual functions. One of them is easy, the other one's a little bit more complicated. All right. So we'll do the little bit more complicated one first. So we kind of look at this as its own separate problem. So here we have some equation, y equals 3x minus 9 cubed. I have a function within a function. Or at least I used to. There we go. So we could use our chain rule there. All right, the u would be the base of that function. And y would be u raised to the third power. All right, differentiate each part. Then it's just a matter of putting it back together. And in fact, I mean, this concept, or at least the difficulty level of this problem, becomes much more manageable if you sort of develop a little bit of tunnel vision. Just really pretend everything else isn't there and just focus on the thing that's important. It's like, okay, well, this is a chain rule problem. We've done a few of these already. That's not an issue. We can handle that. So how is that going to factor into the rest of the problem? Let's worry about that in a minute. You know, all that other stuff's pretty distracting when you look at it for the first time. But the dy dx here is just going to be 3 times the u, which is 3x minus 9, squared times 3. This part, we don't have to differentiate that x. So that's already done. This part, same deal. The only thing that remains is this one over here. Now the notation makes it look weird. But if you write it in a different form, it should become obvious what that results in. Well, what's anything divided by itself? 1. Aside from which, you know, just kind of talking through the product rule, first times the derivative of the second plus the second times the derivative of the first, that first function was x. The derivative of x is equal to 1. So you can kind of talk it out too if you wanted to avoid the notation. I mean, this is more of a writer's cramp type of problem, because once you get a handle on the approach that you take, it's very manageable. It's just, you know, first time through, nothing seems manageable when it comes to this stuff. All right, so f prime of x is going to be, well, I got the x multiplied by 3 parentheses 3x minus 9 squared times 3 plus the 3x minus 9 cubed. I mean, I'll put the times 1, but you don't really need it, I guess. Right? So this just came along for the ride. This just came along for the ride. Everything else was a derivative. You can get a red highlighter in there. A little too red, I think. Too red. Not liking it. Oh, barely anything at all, but can live with it at least. Oh, I forgot the 3. Takes practice and experience. I'm not going to do number 9, but I will get you started on it, just like Tuesday, because anything that is a quotient, because you might think quotient rule. Again, if you haven't reviewed those pages, the videos that I told you to look at, then please do so, because if product rule and quotient rule doesn't sound familiar at all to you, then you're playing with fire. All right. So yeah, it's all in the YouTube playlist. But anyway, this one I would rewrite as y equals x times x to the 4th plus 4 to the negative 1/2. It's disgusting. All right. So when I write it like that, you see it's pretty much the same problem.